Hey everybody, we're going to continue our discussion with standing waves. But before we start this, I want to make sure you guys watch the videos that I recommended you watch before we look at this lesson. If you did, great. If not, I put a link to those videos in the description of this video. So please stop this video and go watch those others before we go into this one. It'll make things go a lot more smoothly. So if you already watched those, great. Here we go. So this is where we left off last time. We talked about standing waves, how they're formed, how to know how many wavelengths in a standing wave we have, nodes, antinodes, things like that. So now we're going to move forward into more the math part of it. Okay, so in this first image here, we've got a standing wave. So very low frequency. It looks like it's just moving up and down like you saw in the videos. Actually, we're probably not going to use this equation. We're going to primarily use the wave speed equation, the general one, and then the one for strings. But anyway, the first thing we want to do is determine how many wavelengths we have present here. So if you remember, we just look at one of these. The string can only be in one spot at a time. So if I draw the whole thing, if we look at this top half, there's one complete wave. So what we have shown here is half of a wavelength. So the length of this string is half of a wavelength, or we can say the wavelength is two times the length of the string, like that. Okay, now I'm going to go to the wave speed equation, v equals f lambda. Okay, now the speed, if we're on a string, depends on the tension and the linear mass density, so I'm going to substitute that in. So square root of the tension over linear mass density equals frequency times wavelength. Well, we have this expression for wavelength in terms of the length of the string, so 2L. So now I'm going to solve this for frequency, and I get F. I'm going to put a subscript there of 1. You'll see why in a minute. 1 over 2L square root of tension over mu. All right. So this F1, we call this the first harmonic. It's also known as the fundamental frequency. There's a U in there. Which means that's the lowest frequency we can get a standing wave. You saw that in the videos. Okay? Now we're going to move on to the next one. Okay, so here you guys should see we have one full wavelength. So the wavelength here is the length of the string. I'm going to go to V equals F lambda. So square root of tension over mu equals this frequency times the wavelength, which is L. All right. So if I solve this for frequency, I get 1 over L square root of tension over mu. So let's compare that to the first harmonic. Here we have 1 over 2L square root of tension over mu. Here we have 1 over L square root of tension over mu. So what do we have to multiply this one by to get to this one? That's right, 2. Okay, so I'm going to call this F2. This is the second harmonic. And F2 is just 2 times F1. It's that easy. And again, you saw that in the videos as well. This is the math showing why that is. Okay. So now we think we might see a pattern. Let's do one more just to make sure. Okay, so how many wavelengths are here? Well, here we've got 1 and then a half. Okay, or if you look at, we've got 3 half wavelengths. Okay, so the length of this is 3 half wavelengths. Okay, or the wavelength is 2/3 the length of the string. And a lot of people just see that right away. It's 2/3 length. Okay, going to V equals F lambda. Again, square root of tension over mu. That's all under the square root. Equals frequency times wavelength. Well, wavelength in this case is 2/3 L. Okay, solving this for frequency, we get 3 halves L square root of tension over mu. Compare that to the first harmonic. 1 over 2L. 1 over 2L is the first harmonic. 3 over 2L is this one, so this must be the third harmonic. So we have F3 is 3 times F1. Okay, again, that easy. All right, so in general, if we want the nth harmonic, that is just n times the first harmonic. So I almost always deal with the first harmonic. It's the easiest one to draw. I only work with one thing, and if I need the 18th harmonic, I just find the first harmonic, multiply by 18, and that's it. Okay, now n is a whole number. Okay, those counting numbers, is that integers or whole numbers? I get them confused, but anyway, it wouldn't make sense to be a negative. Okay, so that's the general idea behind it. You know, you saw in the videos that this is the pattern we should see, multiples of that first harmonic. Okay, so let's go to the next page. We're actually going to do an example with this. Okay, so here we have a mass hanging on a string that's creating tension everywhere in here. We've got the distance here 1.29 meters, and I actually got these because I made this demo at school, which we can't see in the video, but these are actual numbers from that setup. Okay, and then we're told 5 meters of the string has a mass of 1.3 grams, hanging mass is 110 grams, 0.11 kilograms. What is the fundamental frequency on the horizontal part of the string? So we're gonna create a vibration in this part of the string here. Fundamental frequency should mean we see that first harmonic. Okay, so a single standing wave, a single loop, just kind of flopping up and down like that. All right, so that's the first thing I'm going to do. I'm going to draw that first harmonic. Sorry, bad picture. But this, I'll even stick with the L convention here. Okay, this is, you should recognize, a half of a wavelength. So the wavelength then is 2 times the length of the string. Okay, yeah, let's leave it at that for now. Okay, V equals F lambda. Because it's a wave on a string, we can say square root of tension over mu equals F lambda, which is 2L. Okay, and we're looking for the fundamental frequency, so F, that's what we're solving for here, 1 over 2L square root of tension over mu. All right, so we're almost there, but we just have to figure out what numbers to put in here. Well, L is the length of the string. We're given that right here, 1.29, but we need to figure out tension and the linear mass density. So the tension we can get from a free body diagram here, mg, our mass in kilograms, 0.11, and then I'm going to use 9.8 just so it matches my notes on that I posted, because like I said, we had this actually set up in class, so we had real numbers there. Okay, so I'm going to use 9.8 here. So then mg equals I didn't put the mass in there. 1.078, sorry. Okay, and then that's also going to equal the tension, because this is an equilibrium. There's no acceleration up or down, so the tension equals that same number. Now, for mu, the linear mass density, okay, remember that's mass over length, and the mass and the length have to go together. Okay, so we have a mass, 1.3 grams is 5 meters. So 0.0013 and 5, those are the numbers we want to use here. So then we get a value for the linear mass density, 2.6 times 10 to the negative 4 kilograms per meter. Okay, so again, 5 meters has a mass of 1.3 grams. We don't know the mass of 1.29 meters, so don't get that number mixed in here. All right. Okay, so now we're ready to plug stuff in. I'm going to come up over here. So then that first harmonic, 1 over 2L, well, L is 1.29 meters. That's the length that this wave is going to be traveling. Square root of tension, 1.078. over mu, linear mass density, 2.6 times 10 to the negative 4. When we solve this, we should get about 25 hertz. Okay. So like I said, I'd have this set up in class. I'd punch in 25 hertz on the oscillator, and we would see that nice first harmonic, that fundamental frequency, just one big loop moving up and down like that. All right, next, what should be the hanging mass in order to produce 3 loops at 90 hertz? Okay, all right, so a couple options we have here. We could, because it's 3 loops, we should recognize this is the third harmonic. So you can draw the third harmonic and work from that, but like I said a minute ago, I much prefer dealing with just the first harmonic and then adjusting it as I need to. So I'm going to go that approach, and you'll see how consistent it's going to be. Okay. Not the best picture here. Let me move that end. Okay. All right. So again, we've got our length here. That's not going to change. We have half of a wavelength, so L equals wavelength over 2, or the wavelength is 2L. V equals F lambda. So square root tension over mu equals F times 2L. Okay, now this is where I guess we need to be a little careful, is because I'm working off the first harmonic. The 90 hertz here is the third harmonic, so F3 is 90 hertz. But I want F1. Okay, so F1 is just going to be F3 over 3. It's just a third of that. So 90 over 3. So the fundamental frequency should be 30 hertz. All right. Okay, so the tension, if I go back up here, because we want to know the hanging mass. So the tension is going to equal mg, or m times 9.8. So when I go into this equation, I'm going to have m times 9.8 for the tension. M is the unknown. That's what we're looking for. The linear mass density is still the 2.6 times 10 negative 4. That equals F1, which I know is 30, and then 2 times L, 2 times 1.29. Okay? All right, so little math to get to mass, but I would just calculate this right side, square both sides, and then multiply by the 2.6 times 10 negative 4, divide by 9.8. Anyway, the mass you should get 0.159 kilograms, which is 159 grams. So again, in class, I would put 159 grams on there, punch in 90 hertz, and we should see, I'll just do this real quick up here, 90 hertz, we should see, this is the worst I've ever, oh, that's not bad. I've done better. But at 90 hertz, the third harmonic, we should see that pattern then. Okay? And that's really it. Okay? So I would highly recommend you just always work off of the first harmonic. But keep in mind, if you have something other than the first harmonic, you want to get that to the first harmonic. That's what we did here. It's always consistent, and you won't have to worry about drawing a disaster like that. So anyway, there we go. If you have any questions, please let me know.